that expression really is one of the most important of theoretical seismology, because we can assume a medium, and the medium is in G, and we can try to study M. Vice versa, we can try to fix M and study G, so tomography and source inversion. That's the base for any direct approach. Salute. Let's be Italian for God bless you. So the direct approach means, okay, let's build the tools necessary to make some computations. Let's collect data, let's compare them, let's try to invert one of those. Remember that when we switch from the density of a moment tensor to moment tensor, we assume a point source. And for that hypothesis to be working, everything is related to distance. In simple words, it's related by the ratio between the fold dimension and the distance. In more complicated terms, it's also a function of wavelength. So for large wavelengths, history is different than for short wavelengths. But on average, please remember that the far source condition refers to the distance compared to the dimension of the source. Okay? Now, what we're going to do today is to start again from this expression, use the three possibilities that we have now to describe the source as a point, and later today we're going to explore what is G, because we defined it, but we have not found it. And so today, with this cold Monday, we're going to describe G in the simplest case. And the simplest case will be an infinite, homogeneous, isotropic, elastic medium. No surprise there, the Green's function will be related to P and S waves. But we will get a surprise, actually, because we will see that P and S waves are not enough, and there will be a combination of them, and we're going to call the term near field. But in this slide here, we have just near source, far source. If you are in the far source condition, okay, it's a point, so we can squeeze all the information M, capital M, with M0 and ones and zeros. And that's the summary. We can compute a trace of this symmetric tensor. Actually, that trace will be null if no explosion, and the total moment will be null if we consider an internal shear dislocation. So, definitely it has to be made like that, referred to the principal axis. Now, once we solve the eigenvalue problem here, and we can do that quite easily for every second rank symmetric tensor, we can find the eigenvalues, but also the eigenvectors. The eigenvectors are the direction of the principal axis, and they have to be related to plus m0, minus m0, and 0. Now, those axes are called principal axes, and we will start from them today. Just as a final recap, please remember that the moment tensor components, actually, are a system of couples. If the couples have the same indexes, 1, 1, 2, 2, 3, 3, means force is acting in 1 and the arm is acting in 1. So they're like dipoles. If you sum them, you have an idea of an explosion or an implosion. If no explosion or implosion, their sum has to be 0. The diagonal terms are referring to couples, with forces pointing in some direction and the arm pointing in another one. And we will see this game today for a specific particular case, from which hopefully we're going to learn something. So let's complete now the theory, and let's give a look to the three possibilities that we have to describe the source. Do you want me to switch off the light or not? Okay, let's try. Oh, yes. So, now, physically, we have U and Ni. Sorry, Ni should be bold here, but due to tricks with formulas here, I cannot write it in bold. But it's bold. Remember that Ni is describing the normal to the fault. If the fault is a plane, as we're going to assume, okay, Ni is given, just one. And please remember, you will see in the next slide, that the normal of the fault that is describing a plane can also be described by two angles. And they will be the strike and dip. So it's the same. But let's stay now for the principal axis. U and Ni, for a pure shear dislocation, they are, of course, orthogonal. So their sum, normalized, is going to give plus m0. Their difference, normalized, is going to give minus m0. And the axis related to 0, it's called the null axis. There is nothing here except that given Ni and U, we have TBP. And of course, given T and P and B, we can get U and Ni. Just geometry. It's just a different description. We can describe the shear dislocation with the U and the Ni or TPB. They are complementary. Principal axis and U and Ni. Okay, some algebra here will be involved in the next two slides, but I will not ask you at the exam all the formulas that will appear in the next slide. But definitely I will ask you this. Because the concept here is that we have a shear dislocation with a slip vector on a fault plane. Geologically, we can call them the block that is moving hanging wall, the other one, it's a foot wall. Actually, it's nothing else than a relative motion between them. And as we know, we can describe them with strike, dip, and rake. So three angles, plus the absolute value of the slip vector. That actually, it's a heterogeneous field. But now we are averaging everything, okay? Because we're looking at the source as a point source. Okay, we know from the representation theorem that is telling us, okay, you can replace this with a system of equivalent body forces. And a double couple will appear. But another possible description is, instead of U and Ni or a double couple, it's also to use T, P, and B that is coming out from the screen. These are the three principal axes. One word, waiting for the lecture of Wednesday, when we're going to describe what we're going to call a very simple thing that is called focal mechanism, the beach balls, actually. Please remember that what is T for source, that is traction, that is pushing out of a source, for a receiver will be a push. It's reverse, the point of view of the source and the receiver. So what is a traction will be a compression for the receiver. You will see this on weld. What is pressure will be something that is pulling for the receiver. But now, today, we're sit on the fault. So T, P, and B that is coming out. They are totally equivalent to U and Ni, as you have seen here. Given U and Ni, we can get them, and vice versa. There is a third description, and some algebra will be related. The third description will appear in the next slide. But for the moment, let's give a look to maybe the simplest but most important picture of an earthquake. It's this. With a foot wall, we can imagine a hanging wall. Oops, wow, it's perfect. Sorry for that. Okay, We have a foot wall, an hanging wall. I'll try not to do it again, that is moving. We have a slip vector. I modified this Steinway session picture because they are using just a little bit different wording with different letters here, but just to be, how to say, compatible with the other slides, I was putting here a U. That's the slip vector. It has a direction. And the direction will be described by the slip angle or the rake. It's an angle. What about the fault? Well, it will be described by strike and dip. 3 angles. Plus the amplitude of U. That on average is what we call, with square brackets of U. It's the average over the rupture. Okay? What about knee? Well, it's the normal to the fault. And knee can be described with strike and dip. So this is very simple. With some trigonometry, we can get the relation between U and knee in terms of the other 3 angles. That usually are the more geological ones. So strike, dip, and rake can be used to express U and knee. It's just geometry. Okay? Please remember that U has also an amplitude here that is entering into the moment, seismic moment definition. Remember, square brackets of U times the area of the rupture times rigidity. Why rigidity? Because we are considering just a shear dislocation. Okay? Okay, the third and last description. So the first one is using U and knee, or strike, dip, and rake. Then the principal axis, but the third and last is using the seismic moment, plus the moment tensor. So given U that have a physical meaning, a slip, knee, the fault, okay? U and knee are easy. And U and knee can be described by the 3 angles, plus the amplitude of U, okay? With the representation theorem and with the moment tensor description, we can write, of course, the 6 components of the moment tensor in terms of these angles here, plus M0. They are all equivalent. Well, if you want, if you prefer, the only physical description is U and knee. But actually, U and knee will be an expression of the stresses on the fault, TPB. And they are equivalent, thanks to the representation theorem, to a moment tensor, whose components are related to the other ones. Just algebra. M0 is containing the amplitude of motion, the surface, and the rigidity modulus. So you can use the one that you prefer. They're all equivalent. Okay? For a point source. Because the story is not that simple if we consider an extended source. But we know from the representation theorem that actually an extended source can be seen as a set of subsources with a distribution of body forces. And we will see it now. Why I'm showing to you this tricky algebra here? Well, because if you go to, for example, let's see if Binet is working here, I'm not sure. CMT, focal mechanism. But I was putting also the introduction. Yes, let's use that one. If you give a look back to, what is it? This. That was devoted to the Toku event, there was a piece of information here. Okay, still we're missing 2 pieces to understand, to fully understand this picture here, this cartoon here. One will be very important, will be magnitude. But it will be relatively simple. It's coming later. The other feature that we have to develop here will be this representation. We'll do that on wet. But in the meantime, you can see here two focal mechanism estimation, 2-point source estimations, released by two bulletins for Turku. And you see here that you have moment tensor, 6 components. Now you know why it's symmetric. Oops. 3 axes, TPM, that's neutral, okay? My slide it's B. Or strike, dip and rake. Here it is called sleep. Now you could say, but wait a second, it's double. We have 3 here, 3 here. We have 3 here and 3 here. Why? Because it's symmetric. We cannot resolve the ambiguity of a symmetry of a moment tensor. From pure analysis of seismic waveforms, we cannot distinguish between ni and the u in this direction and vice versa. Remember, it's symmetric, so it's the ambiguity. Only one is the source, but we cannot distinguish it from seismic waveforms. It's still related to this symmetry here. This one. Remember, ni and u here can be exchanged. So it's symmetric. Good news, just 6 components, just 3 if you diagonalize it. The bad news is that you cannot distinguish between u and ni. Okay? That's why it's double there. And the same piece of information was on the left for another issue here. Principal axis, 1, 2, 3, but you have 2. Strike, dip and rake, here it is called sleep, but you have 2. You see, and P1 and P2. Which one is the right one? We don't know. And here you have a moment tensor components, 6. It's symmetric. Okay? So what we're missing now is this and magnitude. Let's wait for WED and the other lectures, just to understand what is this. Let's go back to our boring thing here, and let's conclude this part with a specific case. Now, why I'm choosing this case? Oh God, coming back and forth with Keynote. I'm sorry, I hope that in your printing it's not that messy. You have to rebuild them. I guess it's a matter of, yes. Yeah, here it is nicer. I will do it later. What about in your printing? Is that fine? Yes. Okay. Here it is a little bit messy, as you can see. Sorry, it's the new version of Keynote. Expressionist. So, we've seen the general case, and I want you to understand better, I hope, the game of indexes for a specific case. It's a case that has been chosen by Aki and Richard, so you can look at these slides with more, how to say, details in the book. It has been chosen also by Steinway Session. It has been chosen also by Pujol in the paper that I was suggesting you. Now, let's take a specific case. The fault is this one. Well, it's not a fault, but we can imagine that the plane is a little bit strange. It's horizontal, okay? So ni is this one. What does it mean? That, okay, the plane is described by z equal to 0, x and y. So ni has only one component, is z. Okay? Good. And ni1 and ni2 are 0. And the fault is given. So ni is given. And if you want, the strike, well, let's assume that the strike is 0. And dip is given, 0. Okay? So then let's assume that the sleep is in the x direction. From your point of view, maybe it's easier in this way. Like that. Simple. So U is just 1, and U2 and U3 are 0. And it's a pure shear dislocation. Okay? What does it mean? Now, if you take the general expressions that we discussed on Friday, we have seen that the body force equivalent of a shear dislocation, you have to go back to some slides ago, it's like this. Now, this is the general case. This is the vector corresponding to a shear dislocation U on a given fault plane. This is the discontinuity field in terms of slip. This is for a pure, not pure, actually it's for a very general elastic system, could be also an isotropic. This is knee, and these are the spatial derivatives of deltas that are given directions. And that's the fault plane. Now, in this specific case, the integral over the surface is going to be given along x and y. So 1 and 2. U is just 1 there, if you want, for U. Okay? And now, the game between U, that is just 1, and knee, that is just 3, is leaving, sorry for this messy part here, ij to be given. It's 1, 3. But wait, if now we assume that the system is isotropic, the messy fourth order tensor, that is CEIJPQ, is becoming much simpler. Just few elements will be different from 0. And so the next step is that the only two terms that can be alive are just 1313 and 1331. And for a pure shear dislocation, they are just mu. Why? Because there is no explosion. It's our assumption, okay? It's a pure shear dislocation. Good. So what is left there, since now we have PQ just 1, 3 and 3, 1, is this. The equivalent body force of this earthquake is given by these two components. One is acting along X, one is acting along Z. It's not the earthquake, it's the equivalent body force. Okay? Now, that's the integral. Here we have 1, here we have mu. And now if you replace 1, 3 and 3, 1, you will see that we have this a little bit messy games of deltas and their spatial derivatives. Now, we'll see now how they can be represented. But let me tell you that if you perform at the first glance the integration here, assuming a given slip, what we are left is with this and with this. Now, what is this? Well, you see here, one is quite intuitive. This is the average slip along X. Okay? We're left with mu. Okay? Why mu? Because we are considering a pure shear dislocation. After the integration, we will have also an A, the area. So you see that now the seismic moment is there. We have an M0 there. And we're left with some direction. Actually, I should put A here. I'm trying to simplify too much. Now, what is this here? Well, that's a force. And there is a delta that is acting in Z, and the derivative along Z. It's giving us some directions. We will see. What about the other one? Well, the other one is a little bit tricky, because we have a delta in Z, but the amplitude here is not related to the slip, but the spatial derivative of the slip. But we're left with two body forces that we will try to understand now. So the message until now for this specific case is that please remember, once you choose the fault and you choose knee, once you choose the direction of sleep and you choose U, you're fixing some directions. The games of indexes there are making the things much more simpler than the general, because we're left with just two cases here, with two components. Okay? Now let's explore these two. Now, what about the first one? Well, the first one is something that is going to become quite intuitive. Why? Well, give a look. Here or here. What does it mean computing a derivative of a delta? That you are creating an arm. Every time that you take a force and you take a derivative of it, you are creating an arm. So the first set, actually, it's creating an arm along Z. Actually, the first one, before integration, is a set of couples. Running along X and with an arm along Z. Good, it's like this. And they are spread over sleep, over the fault where sleep is not 0. Okay. Now, let's try to compute the total force. Well, if we compute the total force, this means body force, but we have to integrate over all the world of F in the V. Now, with some passages, what I just want to tell you, it's 0 for the first one. Of course, we have a couple. The resultant of a couple is always 0. And we have a set of couples. Good. What about the moment? Well, the total moment cannot be 0 because we have a set of couples. Actually, if you compute the total moment after some very tedious algebra, you will get that the total moment is M0 with plus. Of course, a set of couples will make the world to turn. Like every time that we open a door, we are applying couples. Okay? So for the first set of forces, we have a set of couples with total resultant null and total moment plus M0. Okay, now let's give a look to the second. The second is a little bit more tricky. The second one is this. Now, what is this? Well, let's give a look. We have an amplitude here that is related to the derivative of sleep. Now, let's imagine that the distribution of sleep on the fault, so here, is a curve like that. So it's 0 here, it's increasing, it's 0 here. Okay? So the motion is, I cannot mimic with my hands, something like that. Now it's time to compute the derivative. It's this. The derivative along Z. And now you fill it with forces that are pointing in Z. It's that. Oh, that's not that intuitive, but it's life. If you compute the total force of this will be 0. And the total moment will be like this, but minus. So the end of the story, now if you imagine to overpose these two sets of forces, you will have a total resultant null and a total moment null. Okay? They are not the earthquake, but they can represent the earthquake. Now, in the next two slides, I will show to you that this one actually can be rewritten in different way, just to have a better feeling about that. Because the first one is intuitive. It's a set of couples distributed over the fault. Here they will be 0, here they will be 0. Here the moment will increase according to the sleep. But this one is not that intuitive. There are many ways to rewrite it. And that's an example. For example, let's start from scratch. Let's take the general expression here. That's the representation theorem in the most general version when we have a pure shear dislocation. What does it mean? That we consider that the total real body forces are 0. I know that after weekend you will not remember it. That was the most general expression of the representation theorem. The first term was related to real body forces, gravity, out of the game. This term was related to discontinuities about stresses on the fault, like openings, out of the game. So we were left with this, okay? Okay, let's go back here. Now, there are many ways to write that expression. Here there is another one. Actually, it's the one that I prefer. Please remember, integral over the fault area of a slip, of the properties of a medium, the normal of the fault, and the spatial derivative of the Green's function. Now, what is a spatial derivative? Well, I'm not a pure mathematician, so let's try to make an approximation with a ratio, okay? So actually, this one, after that we have chosen u in the one direction and me in the z direction, is left with this. So the game of indexes here, once that I is 1 and j is 3, is left with just these two elements here. Now, this derivative can be written like that, and this derivative can be written like that. What they do represent, actually, is in each point of a fault, a set of a couple and another couple. Look, the arm here is in Z, the arm here is in X. So the two sets of body forces, once you overlap them, is a set of double couples. With arm in X and Z, and with a moment that depends on the slip. Now I want you to get more confused. There are many other ways to write the equivalent forces. For example, you can choose this one. It's just an example, like that. That's another representation of that shear dislocation. Now, what is the final message that I want to give to you? That in the general case for an extended source, representation theorem can be used in many ways to represent a shear dislocation. We've seen 3. Okay? The one that I prefer, that is the more intuitive, is this one. We can imagine to have a set of double couples instead of a fault and a slip in this direction and in this direction. Okay? We have a set of double couples with moment that will be 0, 0, and maximum where the slip is maximum. Okay? But we have many ways to represent it. All of them are fine. But once we go far from a source and we consider it as a point, all of them collapse in just one possible representation that is a double couple. And that's the final proof. Because if you go now in the far source, what does it mean? Now we see the source as a point, we can compute the integral over the fault, we squeeze it everything in a point, all of them become this. And what is this? Well, this is a force acting in X with an arm in Z, and this is a force acting in Z with an arm in X. So it's a double couple. And as you can see here, actually, the total moment will be null, and the total resultant will be null. So if you want a pictorial version of all this messy thing here, we have many possible ways to represent the same source once we are in a point. For example, in this specific case, with u in 1 and e in 3, the real moment tensor distribution will be this. And once you integrate over the area, it's like that. M0, M0. 1, 3, 3, 1. One couple is this, the other couple, sorry, is this. That's it. And it is this one. Now, 1, 3, 3, 1 are giving us directions of you and me. So the orientation of a double couple in space is remembering the orientation of you and me. What is left is the amplitude of sleep, where it is in M0, because that's the average u and the area over which you perform that integral. And mu is remembering the medium. Once you diagonalize this one, you get this. And you have plus, 0, minus. And you have the three principal axes that are oriented like that. It's the same representation. The last, maybe the easiest representation was the one resembling the fold. Now we can assume that the fold has, well, let's imagine that north is there, so strike is 0, dip is 0, and rake is 0 because it's pointing there. Okay? Good. That's you, that's me. And they can be written in terms of T, P, and B. All these representations are the same. But the equivalent body force, the shear dislocation in the direction with the fold given there, is a double couple 1, 3, 3, 1. If you diagonalize it, there it is. What is left? The amplitude of sleep inside M0. If you can't be in the far source, actually, the fold cannot be considered as a point. But you can always imagine to divide it into subsources for which the far source condition is given, and you can replace them with double couples, subsources, whose orientation in space is resembling the sleep and the knee, but in this case is fixed. And the moment, the specific single moment, is resembling, of course, the amount of sleep on that piece of the fold. But as I've shown to you, well, in the extended source case, the representation theorem is giving many possibilities to describe the source. The source is one. Representation theorem is just a way to represent it. Don't imagine that we have arrows inside. We have sleep. But we can use arrows to represent it. Actually, the final version of an earthquake related to a pure shear dislocation is a double couple, whose orientation in space is, remember, you and me, and whose total moment is 0, but the moment of a single couple is related to M0. This means the area, U, and mu. Now, question. So that's the end for this lecture. What is time here? What is time? Or let's go back to the... Okay. What is time here? Well, there is time. Actually, I was lazy and I was not writing all the dependencies here. But you see there that there is a convolution. So time is there, but which time is left for a point source? For a point source, we have lost all the information about the propagation of rupture. Because rupture was starting in a point, propagating, stopping. What we have left for a point source is just the time necessary to sleep. And we're going to call that rise time. and it will play an important role now. So let me go back to the initial slide of this complicated lecture, because this is what we did. That's the summary. You see, at the beginning we have a, we can call it, the picture of an actual fault with a sleep history of that. Starting, propagating, stopping. And please do remember that here we have time, and also we have an heterogeneous sleep vector in direction. But maybe one is going to prevail one direction. So after we perform the integral, what we are left is with an average area and with an average direction. That's square brackets of U, and that's A. And later we have seen, okay, we can map this into a set of double couples. Actually, just one for a point source. But the only time information that we are left with is just the time necessary for that point to sleep. And it's going to be called rise time. Okay. So what we have learned, we can replace the fault, the faulted medium, we can leave it out and put, in the simplest case, a double couple there. Now you should ask, and now what can we do? Well, what we're going to do today, next, is to start again from this expression that is, as I told you, the most important one, this one. And what we have learned, that at the end of the story, MPQ is a tensor, symmetric, with 6 components, actually 3, the sum is 0, the eigenvalue, blah, 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 and we're left with this. The source and the medium. Now, it's time to look for G. Actually, we cannot just give a look to G, because G, please do remember, and now we're going to start again, it's the Green's function, it's related to the medium, it's the response of the system, linear, to the simplest excitation that we can provide. In our case, for the elastodynamic problem, the simplest one is a single force acting in one point at a given time and in one direction. That's the messy thing. And we can imagine that according to the direction, this one, or this one, or this one, we will have different feelings. So if I'm going to hammer in this direction, or in this direction, the motion will be different. So we are waiting for a radiation pattern. Okay? It will not be a surprise. It will be a little bit difficult, but we have to wait for a radiation pattern. But we will get a surprise. Second, let's please remember that once we solve for G, actually that's not enough for an earthquake, because we have to compute actually a derivative. We have to compute couples. So the expression will not be just G, but its spatial derivative, because we need to describe a double couple. Is it okay up to this point? Okay, now let's try to solve the problem of the elastodynamic Green's function. Here I will just reproducing the general view of the Green's function. You can invoke the Green's function every time that we have a linear system or something that is described by a linear differential operator. Green's function is everywhere, from quantum mechanics to electrodynamics. In our humble case, it's just the elastodynamic Green's function. So for a classical physics problem, with some complication arising from directionality. Let's also remember that once we find the Green's function, we can use it to write the general response of that system, just with convolution. That's the general property of the Green's function. But that's why I was here invoking again the general linear system theory. Let's spend just 1 second to give a look to it because it's a sort of proof. We can imagine that a linear system is just maybe dependent upon just one variable, for example, time. The characteristic is that the answer will preserve multiplication by scalar and addition. That's the general definition of a linear system. Now let's imagine that we input a generic x of t. We can always write x of t in this way here, with a convolution of deltas. Pure mathematicians do not like this because delta is not a function, it's a distribution, but let's imagine that we can do it. Okay, once we input this, since the system is linear, the integral is just a sum of something times deltas. And if we know the answer to a delta, and we call it impulse response, or Green's function, so it's h, well, convolution is nothing else than multiplication. It's a product. What does it mean? That this multiplication will be preserved, the sum will be preserved, so the general answer will be this. If we input x, we will get a y that can be written by means of h, like this. And if you do the Fourier transform, the convolutive product will become algebraic product. That's why it's easier to perform filtering with a frequency domain. Okay, h here, usually it's called impulse response. We can call it the Green's function. Now the bad news is that we have to solve this differential problem. That was the definition, okay, that we have used in the last lecture. So we defined it. The Green's function is the solution to this problem here. These are the general equations of elastic motion for a general anisotropic system. And it's an inhomogeneous problem when the inhomogeneous term is the simplest one. But we have space, time, and direction. So space, time, and we have to decide, okay, G is the answer in the x, y, and z direction. That's the first index. When the force is acting in x, or y, or z. That's why it's a tensor. Okay. Now, what we're going to do today is to take a shortcut inside not a trivial solution. The solution was given by George Green or Robert Green, I don't remember. The general idea was by Green, that was a beautiful mathematician, English mathematician, long time ago. Then Stokes was acting on this and Love was acting on this. There is a lot of algebra here. But as you know, I'm lazy. So we will just take the milestone of this path through algebra. So let's, like in the case of the representation theorem, I will not ask you all the formulas that I've shown to you there, but the logic. Okay, so please remember what is a representation theorem, why it's called representation, what's the end of the story, and how to go to the end of a story with a double couple from a logic point of view. But if you want to remember all the formulas, you are very welcome. I will ask you just the main ones. So Mij with the convolution of NP, Q. Now, the same message applies today. How to solve this? Well, you can say, come on, we solved this problem when there was no inhomogeneous term. And what we have found for an infinite elastic isotropic medium, just P and S waves, if you do remember. Very simple. So P and S waves have to be the ingredients to be cooked for the recipe of the Green's function. They have to be there. In general terms, when you want to solve an equation, also a differential one, what we have to solve is the general case, general homogeneous, and the specific solution of the inhomogeneous. Then you solve. That's the tricky part. Okay, let's start to solve this problem here, but as a training for a simpler case. What is the simplest case that you can imagine of a homogeneous term? Well, actually, a delta in time, in space, but no direction. It would be very nice if we have to study beautifully isotropic, but in a sense of force, explosions. So we have a symmetry there, a radial symmetry, of course. Well, that solution is simpler, and we are going to give a look to that, just to have a flavor of what we have to find later. So, let's try to solve the inhomogeneous wave equation in the simplest case. Well, the differential operator of a wave equation is something like that, where c is velocity, this is the Laplacian, where in 3 dimensions, we know, okay? Velocity is the same, it's homogeneous, it's isotropic, everything is beautiful, but with delta in x of t, and we're in the center of the coordinates. If you want, this explosion can be seen with the moment tensor as 1, 1, 1 on the diagonal terms. All equal, all positive. Implosion will be all equal, all negative. Okay? It's a specific case. It will have a radial symmetry. And since it has a radial symmetry, the solution will be easier. Now, again. Actually, what we should do there is to solve the Helmholtz equation, or Poisson equation, if you want. But since I'm lazy, we will skip this part, and we will just get the solution of this case here. Well, the solution has a symmetry, of course. We have some normalizing factors here, but if we have a delta like that, it was not that symmetric, but if we have a delta, we can imagine propagation. A delta will propagate, but we will need to take care about the retarded time. We have to wait for the perturbation to reach the receiver. And that's why the solution is like that. So a delta at the source means that we will hear a delta. It's homogeneous. Please remember, we have no reverberation in there. It's free field. Okay? So delta starts, delta arrives. How much should we wait? Well, it depends on the distance. And then we will hear the delta. So distance divided by velocity. And please do remember that for spherical waves, the symmetry, the spherical waves, will tell us that for the energy to be conserved, amplitude has to be decayed as 1 over r. Spherical waves, not plane waves. Spherical waves. If you do remember, we treated them in wave physics. Okay? Good. And the problem is pretty much solved. It's not but difficult. Why? Because we have a huge symmetry there. We don't have directions. No one is kicking in one direction. If you want, that's the acoustic important case. Okay, so delta is a rapid function. Delta will arrive with a retarded time. From this property here, actually we can also derive some additional properties. For example, what if we move a source in space and time? Well, that's not a problem. What is really important is to use our clocks starting from the delta, when the delta is starting, so the retarded time has to be considered at a proper time. And, well, we have to make a translation in space. But that's not. Nothing is changing here. What is important is relative time and relative space. Okay? Easy. What is also nice, since the system is linear, is that if we are not playing a delta, but if I'm singing like a tenor, what you're going to hear is the tenor. Not like me. Why? Because here we have convolution and it's a linear operation. So if we have an f of t will arrive at the proper time, at the proper space. And if the distribution of the source is homogeneous, we can also imagine to have an extended spatial source if we are able to write the extended source as a sum of subsources, that is what is going to arrive. Because everything is linear. What does it mean? This, that if we take into pieces the source, well, what we have to do is to do the integral of the single contributions. It's like in optics. Okay? So no news here. It was just a training to understand what a delta is. So if we have a very simple acoustic case in the free space with atmosphere, otherwise no sound, and we do something like that, well, we have to wait, and our acoustogram will be just a delta at the proper time with an amplitude that is decaying with distance. But no radiation pattern. Why? Well, radiation is isotropic. So we have a spherical symmetry around the source. Is it okay up to this point? Okay. That was just a training to relax. Because now we have to go into directions. That's the messy thing. Again, you can find the full development of this part in the Aki and Richard's textbook. As you have seen also from this picture here, sorry, let me use it again, this one. This part is covered also, this is coming from a Steinway session. Oh, you can relax, okay? Now, let's go to our problem. Before going back to the Helmholtz theorem, let me remember to you what is our problem. It's this. It's a delta in space, okay, did it. Delta in time, okay, did it. But the difference with respect to the explosion is that now the delta is acting in one direction. Okay, so the problem is more complicated, and please do remember that for a seismological case, we don't have just sound, like in the acoustic case, for air or liquids, but we have shear and compression. So we have to wait for P waves, yes, but also S waves. Okay? Now, how to solve this problem? The problem was solved by Green and Stokes. Stokes' trick was to write this term here, the source term, if you want, using the Helmholtz theorem. Now you could say, what is the Helmholtz theorem? No, but at least three of you should answer to me immediately what is Helmholtz theorem, because we used it at the time of the Navier equations, so the equations of elastic motion, and we solved the problem separating the P and S waves, if you want. Because the P waves were related to the gradient of the scalar potential, the S waves were related to the curl of the vector potentials. Then we separated into P, SV, SH. PSV became Rayleigh, SH became Love. We used Helmholtz theorem. What is saying Helmholtz theorem? Well, we can spend a course, not for me, but we could spend at least half of the course debating about Helmholtz theorem. But the main message of Helmholtz theorem is that every polite vector field can be written as a sum of the scalar potential gradient and curl of the vector potential. What was the Stokes trick? Well, since we can decompose the wave fields in scalar and potential, let's also decompose the force in scalar and potential. The hope is to separate the complicated problem into two simpler problems. And it was right, of course. So, the beginning of the story is this. It's Helmholtz theorem. Here I'm just reproducing the slide that you have in the wave physics course. Do you remember it? Is it a yes? So what's coming now? Don't read. Just a trace of the proof that I was proposing to you at that time. The proof was related to the Poisson equation, because the game here is, okay, I give to you U. Can you find capital phi and capital psi? Then the game that you have to play is, okay, let's consider Poisson equation of a general W related to U. You solve it, and you got this solution here. That is very similar to the Helmholtz problem that we solved for the Green's function with an isotropic problem. Okay, once we get W, and it's algebra, so we have to compute the volume integral of U, blah, 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 we can find the solution using this identity. Because the Laplacian can always be written as the gradient of a divergence minus curl of a curve. You could say what? Okay, now this can be written like that, and we can find that actually the scalar potential is the divergence of W and psi is minus curl of W. And we're lost now. Just to let you to remember that once that U is given and we can compute this integral, we can find the two potentials. Just recap of the Helmholtz theorem. Ish. Very few words. If U is polite, we can find phi and psi. Okay. Let's go now. Oops, that was supposed to arrive later. Yes, that's a nightmare. It was a nightmare for me to write it. But let me just tell you. Let's try. No, let's put things. This should appear at the third. Otherwise, it's tragic. Good. Better. What do we have here? That's the real starting of this part of the lecture. Well, we have to solve that equation. Now, for those of you who attended the wave physics course, it should be your good old friend. Let's see if I'm able to find it. By name, elasticity. Missing font, okay. Strain, stress, generalized Hooke's law, elastic constants, and here you go. This was the equation of motion in the case of homogeneous medium. That was the spatial derivative of the stress tensor. My God, all the things have been messed up here. For a homogeneous system, lambda and mu do not depend on space, so we can take out from the derivatives, and what we found was this equation here. That was a nightmare, but then later we said, okay, come on, let's use some vectorial algebra. We can rewrite it like that. And actually, in the next slide, we were separating P and S, taking the gradient and taking the curve, divergence and the curve. Now, F at that time was there to represent body forces, like gravity. But then we said, come on, who cares about gravity? Now we want to study elastic motion. And we throw it away. Well, today we have to keep it away, because F will be needed to find the Green's function in order to represent a shear dislocation. Okay? But it's that equation. Okay. So what we left at the time now is reappearing. You see how actually the other terms are separating divergence and curl, P and S. No, that's the problem. F. So let's imagine that the body force terms can be separated using Helmholtz theorem. So we write it in these terms here, and now the game is to find the scalar and vector potential to represent F. Okay? Of course, we have to express initial conditions. For example, the force will act at time t, so it will be 0 first and later at a given time. In a given point. And it's polite. Okay, then we can find two potential with the following properties. Now, the Lamé theorem is saying, let's take this equation, let's represent f with Helmholtz theorem, then this equation is becoming this. You could say, oh, and so what? Well, we decomposed one complicated equation into two complicated but less equations. Because U can be written as a combination of the gradient of a scalar potential plus the curl of a vector potentials, and the two potentials have to obey this equation. Wait a second, if we remove the source, they are still P and S waves. Okay? So the news here are here and here. But now we have broken the equation of elastic motion into two parts. Thanks to our laziness, Stokes will intervene here and will solve the problem. Now, just to have a flavor of directions here, how Helmholtz theorem is working for the source terms. For example, let's imagine that f is given. It has a given amplitude. It's acting with a function that is a function of t. So maybe I can also do something like that. You can imagine it to be a delta. So like that. In a given position, in a given direction. For example, x. Okay? The game is to find the two potential to write it. Well, we have to write the Poisson equation for this problem here, but now you see some indexes will become easier. That's W for this specific force. And now we can find the two potential computing the divergence and the curl. Those are the two terms to be inserted in those equations to be solved. So that's the specific case of this general problem here. Let's try not to miss the logic. The logic is that we have to solve this equation here. Let's apply Helmholtz theorem to f. Then the problem is separated into smaller ones. Still not homogeneous, with phi and psi described by the force. And in this specific case, those they are. So now you can imagine to take this term here and to plug in into the first, this term here and to plug it into the second. Okay, now the next part is just algebra. Algebra that will give us directions, in the sense that if I'm going to kick into x1 like that, and if I apply the force here into this direction, I should wait for p waves of a given amplitude here, of p waves of a given amplitude, imagine that the table is extended here, and since they are compression and rarefactions, maybe I shouldn't feel them here and here. Okay, so maximum will be there, maximum push, maximum pull, nothing, nothing. What about shear? Well, let's wait for 0 here, and maximum here, because shear is complementary. So we are going to discover the radiation pattern that is related to directions. So it's like in optics, if you have a photon source, photon emitter, or like a lamp, if I point you in that direction, you should wait for the maximum of the radiation in front of you. Okay? Or like an antenna. Antenna, when it's emitting radio waves, has lobes. Okay? According to how you set the dipoles and stuff like that. But the radiation from an antenna, EM antenna, is not isotropic. We have lobes. That's engineering, how to study, to receive and transmit, okay? These are the lobes that we are waiting for forces. And they will be separated for P and S. This is what we are waiting for. And this is what Stokes did for us. The next expression is very important. And actually, what is just embedding are directions. Because once we have solved the Helmholtz theorem for the body force, we have placed in the two equations, now it's matter to be a very good mathematician and to make some algebra. Let's try to use intuition, and we can imagine that all the spatial derivatives there will give us direction cosines. And you will see that in this case, the direction cosines will give a relatively simple radiation pattern. Is it nice? No, it's not. But it's nicer than to compute it. So let's trust Sir Stokes and let's give a look to it. What is this? Well, first of all, x0 is not important. x0 is the time function that we apply in that point. It could be a delta. If it is a delta, convolution of a delta, it's just the Green's function. Okay? So x0 is not important here. If you take a delta, it will be a delta. Good. What is ui? Ui is the component, it's a vector, it's the vector of displacement, x, y, z, given a force in J. Okay? Good. Let's forget about this for 1 second. It's going to be called the near field term. It is the surprise. Don't look at it. Let's give a look to the other two. They are called far field terms. Now you should ask, what is near, what is far? The answer is here. Cubic, in this kind of writing, just 1 there. What is that one? Well, the absolute modulus of x is nothing else than the decay that we are waiting from spherical waves. We are waiting for that. It has to be there. Okay? What about this? Well, this is the normalizing factor for p and s waves, alpha and beta. Please do remember that we are now considering an infinite, homogeneous, isotropic, perfectly elastic medium. Okay? So we understand this, but we also understand this. Because what we have to wait is to wait for a p wave that is traveling with velocity alpha, and is nothing else than the usual writing here. And the other one is traveling with beta. Those are just p and s waves, of course. What is this? Well, this is the radiation pattern. This is what we were looking for. You will see in the next slide how easy or intuitive it is. This product of these things here is nothing else taking care about the derivatives around space and will give us just sines and cosines. Very simple. Something that is not simple is this. Because we were not waiting for that. We were waiting for a p, and here we have, for an s, and here we have, spherical, and here we have. But what about this? We don't know. Yeah, we're going to write it now. But definitely it's decaying much faster. That's why it's called near field. It's not easy to separate the near field from the far field. Remember, this is not near and far source. Now the source is a point. Okay? So it's something different. It's something that when we are so far from the source, but now is a point, well, this is negligible compared to this. Sooner or later, this term will dominate. It's not that easy. If you want, before I forget, for the near field to be considered small enough this has to be larger than 1. Now, what is k? Well, so when the distance will be much larger than the wavelength. This is just a rule of thumb, but I don't want to spend a lot of time here. So, okay, we found the Green's function for a homogeneous, infinite, isotropic, elastic medium. We'll see later in the course that when the medium is not elastic, here we will have to add some inelasticity. So amplitude will not just decay as 1 over x, but part of the energy will also change due to the fact that some energy is absorbed by the medium. But for today, it's perfectly elastic. Now, let's give a look to the far field, so the blue one. Well, it has the properties that we were waiting for. It's decaying as 1 over r, spherical waves. It's made of P and S. Of course, we're in an infinite homogeneous, so no Rayleigh, no love, nothing is here, just P and S. We have to wait for the retarded time, and it has a radiation pattern. This is what we were waiting for. Now, if you write the radiation pattern, it's a little bit messy, but let's say that the P depends on cosine. So let's imagine that we apply a force in this direction. Let's imagine a lobe of a cosine like that, positive and negative here. Okay? 0, cosine is 1, and here it's decaying. So we have 2 lobes, positive and negative. With intuition, we can imagine that we're going to get a kick there and a pull here, okay, if the force is applied in this direction. Nothing here. If you give a look to the S1, it's sine, so we have 2 lobes here. One will be in this direction, the other will be in this. So it's simple. And actually, we can also write now the first seismogram due to a source inside the Earth. Well, the Earth is boring because we have no boundaries. It's infinite homogeneous and infinite elastic isotropic. What's going to appear here? Well, according to our distance from F, we have to wait for a P, a bump, could be a compression or a dilatation, with an amplitude that will depend now on the relative position with respect to the direction of the source. Okay, that's the radiation pattern. On average, amplitude will decay as 1 over r, spherical waves. And that's a plot of the radiation pattern. If F is pointing there, you have a maximum here plus, maximum negative here, 0s. What about S? You have to imagine 2 lobes here. Good. So, thanks to Green, Stokes, and Love, that's the solution. We're done. But wait a second. There is an additional term that actually, when we are near to the force, is there. We cannot neglect it. And it's this one. That's the near filter. That's the surprise. Well, if you write it, if you develop it, you see that it has a radiation pattern that is similar to the S1, but actually it's made of 2 contributions, and it's a mixture of P and S, because it's arriving after P, but it's not just a delta. It's continuing there, and then it's stopping. But wait a second, because it's stopping without going back to the equilibrium. Because actually, it depends on the radiation pattern, so if F is like that, it's more important here and here. It's decaying faster, cube and square here, okay? So sooner or later, it will be much less than the far filter that we have seen. But if we are near enough that these terms are still visible, well, they are made of P and S, and that's important. The end of the story is that the pen of a seismogram is not going back to the equilibrium because it's tilted permanently. What does that mean? That once a force is active like that, so you apply a force here, you don't come back. That's not a single force. It's like that, okay? Something is left around that is making the system not going back to the equilibrium. You can call it coseismic displacement. It's not still the coseismic because we have just a force. But something is left there. Sooner or later, well, far, actually, it's going to vanish. But near to the force, it's there. And it has a static component. Now, when you're going to start the course with Alessandro Borghi, you're going to study coseismic displacement. And from the point of view of geodesy, it's something that can be measured with a GPS, because you are at an equilibrium, and if you are near enough to the source, something is not going back to the equilibrium. It's not like acceleration. Something is left, and you can measure it. Well, the formula that you can use to interpret the signal is this one. You should say, no, it's not this one. Because we are still missing a piece. Because with this slide, we can say that we have solved the Green's function problem. So the solution of the Green's function is this one. Good. We did our job. Well, we are missing one part. Because for an earthquake that is a pure shear dislocation, the Green's function is not enough. That's the answer to a force. Now we have to take another one and another two, if you remember. Because we have to take that formula, as before, m0 convolved by the spatial derivative of the Green's function. m0 minus m0, or if you want, m013, m031. Each of them has to be convolved with a part of a moment tensor if we want to represent an earthquake. So we can say, okay, that's the Green's function, but for the earthquake, that's not the end of the story. Let me show to you again that expression. Oh my God. Look at this. Now what we have to do is to take G and P, Gij if you want in our, and to compute a spatial derivative along Q. It's creating a couple. Then we have to take the other one, and we have to make the permutation between P and Q. So in the specific case that we treated, MPQ was this one. 1331. So we have to take this term here, 1, 3, 1, 3, and now we have to compute the derivative and consider a couple in this direction and another one in this direction, because we have to solve this problem here. So we have to make a further, maybe final step, algebraic step. We have to compute the derivative. That's why the Green's function is not enough, but we have to compute this. Actually, what we have to do is to compute this. So please remember, n is the vector that we want to model. U is the vector that we want to model. It has 3 components. N can be 1, 2, 3, x, y, z. Okay? Now, given n, is the first term of a Green's function, x, y, z. But the source, the guitar player is playing in PQ and PQ. So in our specific case it was 1, 3, so 1, 3. Now we have to take, for example, x, x, and here we have to derive along z, the arm along z. The other one is 3, 1, so the Green's function is pointing along 1, along 3, and the arm is along x, the double couple. The expression for the double couple is this. You could say, oh gosh. Well, wait a second. The blue should relax you. It's what we were waiting for. Because it is made of a P wave and an S wave. It's propagating as a spherical wave, good. With radiation pattern that is more complicated, because the radiation pattern that we have seen before is for a single force. Now we have to take a single force, compute an R, and compute this. Then to compute this, take an R, and compute this, and to sum. So radiation pattern is more complicated than the one of a single Green's function, of course. That's the price to pay. And this is what we're going to use on Wednesday to study focal mechanisms. Point source, far source, and into the far field. Just those ones. And we will create the tool to create focal mechanisms. But please do remember that there are two additional terms. But now they are a little bit more complicated. But still they have the same meaning as the near field in the first case, because they decay faster than this term here. Well, one is called intermediate because it's between 4 and 1. Okay? And those ones, actually the yellow one, is the one that you are going to study with Alessandra Borghi. The situation is a little bit more complicated, but okay. If you want to write it fully, there you go. So you have a near field, a far field, and, near, intermediate, and far. We are going to use this one. As you see, it's still a combination of sine and cosines. Why we need two angles? Because now the double couple is oriented into the space, and we are a receiver here. So we will use a reference system that will be centered into the source, and we will describe the radial component and the shear component. And we will need three angles. We will see this in the next lecture. But please do remember that we have other two. Radiation pattern of a double couple in the far field will be the topic of the next lecture. But let me tell you, and that's the reference system for the source, as I was telling you, that you have something that is left static there, that is in the near and the intermediate term. If you want, that's the expression that maybe, but Alessandra maybe hates mathematics, maybe not. This is the one that you're going to interpret when you're going to use the co-seismic displacement. What does it mean? Okay, part of it is going as radiation, like P waves and S waves, but part of the energy is left in the co-seismic displacement. For example, if you take the reference system of a specific case that we considered in the specific case of the representation theorem, you see, it was something like that, we can use this reference system here, and one angle is giving, if you want, the co-latitude of the receiver. The other angle is giving the longitude of the receiver. And the third term is giving the distance of the receiver. If you want, it's the spherical reference system that we have used for the normal modes of the Earth, but now it's centered into the source. It's easier to understand radiation pattern. Well, if you have this double couple, that's the co-seismic displacement that is left around when you see it from there. So that's the double couple, 1, 3. If you see it from your point of view, the arrows that are left there are like this. These are not going back to zero. And you can use them to study co-seismic displacement. This is what you're going to do with Alessandro. This is L'Aquila earthquake. So the fringes that you're seeing there can be computed with DINSAR, with differential motion or pictures of the satellites. And what is left there? You see, after some space, it's zero. It's left. These are the fringes of Haiti event. And please do remember that if you have a GPS, and if you're there, let's imagine to have a subduction like Toku, you have the accumulation of stress. It's playing with against friction. Friction sooner or later is going to lose. You're going to have the sudden slip on the fault that we can represent. And if you imagine to have a GPS here, later, at the end of the story, it will bounce again, but it will not go back to the equilibrium. But you have to be near to the source. And actually, if you give a look to the introduction that I was showing to you, you had it there. And now I'm going to close. You want to see it? Very well. Look here. You see that in the displacement, the pen is not going back to the equilibrium. But if you are far enough, it's not there. And you have just what you can call the far field. But if you're near, you're not going back to the equilibrium. Of course, if you compute the derivative velocity, it will disappear because it's zero, a constant, but it's not evident in velocity or acceleration. It's evident into displacement, GPS. So that's the part that you're going to explore with Alessandra, but maybe also with Karim. And this was the co-seismic displacement left after Toku. Now, to interpret them, you can put there, of course, a thrust with a strike, dip, and rake, and you can compute it. You can make predictions, you can measure it, and make some inversions. And this is the part that we're going to study on WELD, that is the radiation in the far field for a double couple. What does it mean? Far source, far field. The source is a point, and it's a double couple. We will use the formulas that you've seen before, trying to predict the motion at a set of receivers around the world given an earthquake that again can be described as a point source and with a double couple. This is what we're going to do. So focal mechanisms. If a Green's function is described by lobes of sine and cosines, actually the radiation pattern in the far field for P and S waves will be described not by 2 lobes, but usually by 4 lobes. But you will see differently according to your relative position with respect to the orientation of the double couple, radiation pattern. But we are going to wait for an S wave, for a P wave, for an S wave, propagating as spherical waves, and whose amplitude is decided by radiation pattern. There is one last detail, but we will discuss it on. That the spatial derivative actually is going to give also a time derivative. Please remember that that dot is not a bug on the screen, it's not a bug on my slides, but it's the time derivative of n. Now, a thought for you until Wednesday. What is the time that we have inside n? That's my question. That's your homework. Because if it is a point, we have just one time.
Rise time.
Just rise time. But then, what about its derivative? Think about it. We're going to do that. The answer is simple. But up to now, for a point source, we will be left with just the time derivative of this. Maybe it's not enough. Maybe. So, okay, what we did today